Now that we've had an introduction to nuclear fusion, we'll address the other two types of nuclear reactions, nuclear fission and radioactive decay. We'll begin by looking at nuclear fission. Nuclear fission is the fragmentation of heavy nuclei to form lighter, more stable ones. When fission occurs, energy is released. There are many possible ways to break nuclei apart. Here, a neutron hits a uranium-235 nucleus, the main component in atomic bombs, which breaks it into two lighter nuclei, and 3 neutrons are also released. This could be a bit of a problem. Each of these neutrons can potentially cause another fission event. If the number of neutrons released isn't controlled, this can start a chain reaction. The stability of a nucleus depends on the ratio of neutrons to protons, along with the overall size of the nucleus. Too many or too few neutrons can make the nucleus unstable. So nuclei that are unstable may undergo fission, wherein they split into a number of more stable, smaller nuclei and possibly releasing some neutrons. These neutrons can then go on to cause more fission reactions that can lead to a chain reaction, since each unstable nucleus could release multiple neutrons that are capable of initiating a fission reaction. The mass required for a chain reaction to become self-sustaining is known as the critical mass. The image shown here shows a chain reaction for uranium-235, which is an unstable isotope used in both nuclear power reactors and nuclear bombs. In order to get the concentration of uranium-235 high enough to use it for a nuclear power generation, we need to enrich it to reach a critical mass. Below the critical mass, the likelihood of a neutron being captured for fission is low. Above this, the chain reaction becomes self-sustaining and can go out of control. In a nuclear reactor, there are rods that absorb the neutrons, keeping the reaction under control. Nuclear bombs are designed for the chain reaction to go out of control and explode on purpose. All of this brings up the question of how can fusion, the merging of nuclei, and fission, the breaking apart of nuclei, both produce energy? To answer this, we go back to stability. Remember that stability depends on the number of each nucleon and the size of the nucleus. The most stable element is iron. Lighter elements become more stable when they fuse together, but remember there's a huge energetic barrier. And heavier elements decay to form more stable, lighter elements. The nucleus of iron is the most stable, thanks to its favorable surface area to volume ratio. Energy is released as lighter nuclei fuse to move toward that ratio. Energy is released as heavier nuclei undergo fission and break apart to get to that ratio. Eventually, iron should be the only element present in the universe. Don't worry though, that's not predicted to be the case for another 10 to the 1500 years. The final type of nuclear reaction we will discuss is radioactive decay. In each type of radioactive decay, the nucleus emits or captures particles or energy, resulting in a more stable isotope. The common types are alpha particle emission, which involves a helium nucleus, beta particle emission, which involves an electron, and gamma radiation emission. Alpha radiation includes any radioactive decay that emits an alpha particle, which is essentially a helium nucleus. Remember that Rutherford used alpha particles emitted from a radioactive isotope in his gold foil experiment. Here, an example of a radium atom undergoing alpha decay is provided. Beta radiation includes any type of radioactive decay that results in the emission of a beta particle. Provided here is an example nuclear reaction of a radium undergoing beta emission. Gamma radiation is something that can occur along with the other two types of radioactive decay. Gamma radiation is a high-energy photon that is often emitted along with alpha and beta particles. An example here is provided. Notice in this reaction both an alpha particle and gamma radiation are both emitted.